Hi, I'd like to try doing a triple integral with you. Here's what I'm interested in, like the triple integral of this function, x squared plus y squared, say dv, over some region, or say some solid that we'll call E. And the solid I'm interested in is the shape that's bounded from above by z equals 2 and below by z equals the square root of x squared plus y squared. So you have to kind of figure out what this object's going to look like. I'll do my best here. But if we draw the x, y, z axis, then we know this first equation, z equals 2, is just a plane whose height is 2. So this is equals 2. It's parallel to the xy plane. This thing on the other, this second shape sometimes causes people a little bit of issues. Nice way to do it is try and think about some values that would be, say, easy to see. So for example, if z equals 0, then obviously x has to be 0 and y has to be 0, because those are the only numbers that when plugged in here would return a z value of 0. Additionally, we're taking the square root of x squared plus y squared, which will actually be positive all the time, so that's good. We know we're only going to get positive z values back because when you take the square root of a quantity, it only returns positive z values. Or square root of anything, sorry, it only returns positive values. All right, that said, what about z equals 1, for example? Well, if z were equal to 1, you'd have 1 equals x squared plus y squared, and you have the square root here. You could square both sides if you wanted, and you'd get 1 equals x squared plus y squared. Well, clearly that's a circle with the center at 0, 0, and a radius of 1. So 1 squared here if you want. And it's got a height at z equals 1. So we'd go up to z equals 1, and we'd have like a little circle here of radius 1. And it might look like that green circle's in the plane, but I was attempting to draw it slightly below the plane, so it's not so great. Okay, let's consider z equals 2. Obviously, that's the intersection between these two things. So if z is equal to 2, then your equation becomes 2 equals the square root of x squared plus y squared, or 4 equals x squared plus y squared. Well, that's just a circle of radius 2, but on the plane, z equals 2. So you end up with this bigger circle up here. And if I did a better job drawing it, you'd see something that ended up looking like a cone. It might be worth our while to go draw this in an online graphing program. So let's go do that. Okay, so I happen to have that ready over in a program called Desmos. So here's what it looks like. You can kind of see it if you look at it from different angles. Desmos is pretty cool. So just search, I'm sorry, not Desmos. This is GeoGebra. Search up GeoGebra 3D and you can graph this kind of thing. So you can see it's a cone. So what we'd like to do now is set up the triple integral. Well, one thing you should do is consider the shadow this thing makes into the xy plane, and you know that's a circle, x squared plus y squared equals 4. So here's a way to help you set that up. So let's say you have your xy axis. Here's x squared plus y squared equals 4. Um, and we know this cone is sort of floating up above this with the tip of it right here at the origin. All right, so let's start to write out our triple integral. And when they say dv, you kind of have to decide upon an order. Say we decide we're going to do dz, dy, dx. And the thing we're integrating is x squared plus y squared. Okay, well, z is always going from the lower, on the lower side, that cone, which has the square root of x squared plus y squared as its equation, up to 2. So that's really not so bad. Z was bounded for us from the beginning. It's the y and x part that we got to think about a little bit. Well, y is going from the lower semicircle here, which I've highlighted in red, to the upper semicircle here, which I've highlighted in blue. So the square root of the upper semicircle is the square root of 2 minus x squared. And the bottom one is negative, the square root of 2 minus x squared. And then this is all going to happen as x varies from negative 2 to 2. Okay, so this all looks good and so forth, but when you start to see pretty wild looking limits of integration with square roots and x squareds in them, you sort of know that maybe we can change to a different coordinate system. Here you can see that our base region is a circle that's very easy to describe in what's known as polar coordinates. In this case, we could say that the radius is always between 0 and 2, and then theta is always between 0 and 2 pi. So it seems worth it to rewrite this in polar coordinates. So that's what we're going to do. Don't forget also that x is equal to r cosine of theta and y is equal to r sine of theta. So fun little algebra. If you have x squared plus y squared, that's going to be r cosine theta squared plus r sine theta squared. You square both components here, you get r squared cosine squared theta plus r squared sine squared theta. And you can see that common factor of r squared. So if I take that out, I end up with cosine squared theta plus sine squared theta. But that's just 1. So you just end up with r squared. That's really nice. You could also see it geometrically. So for example, if r is the distance from the origin out to your location, then the horizontal piece is x, the vertical piece is y, and you could just do Pythagorean theorem. X squared plus y squared equals r squared. So whichever way you like. So what does that mean? It means our triple integral, we're definitely integrating r squared. You're going to have a dz, d theta, dr. Don't forget you need to multiply by this extra r here. This is a correction factor. I'd have to make another video for that if you wanted to see why that's true. All right, so v is still varying between, we know that z's lower bound is this thing. But that's really r, because we just proved a moment ago that x squared plus y squared is r squared. So that means this thing starts at r and goes up to 2. So those are nice limits of integration. Theta is going to go from 0 to 2 pi, so you can span around the whole circle. This would be 0, pi over 2, pi, 3 pi over 2, and then back to 2 pi. And then lastly, r is going to go from 0 to 2. And this integral is nice to calculate. So let's do that. Let's just erase this for a minute, get that out of our way, and let's do this inside integral. So this is really r cubed, but if you're integrating with respect to z, then r cubed is a constant. So the antiderivative just becomes r cubed times z, evaluated from r to 2. So if you plug in 2, right, what do you get there? You get, looks like you get 8, and then minus, I'm sorry, that's not correct. We're plugging in, see, I made an error. You're plugging in 2 to z. That's, you got to be careful of. Easy to make that mistake. So then you end up with 2r cubed minus when you plug r into z, you get r to the 4th. And that's a reasonable way to leave it. Why not? Okay. So now we're going to do the next integral from 0 to 2 pi of this function, 2r cubed minus r to the 4th d theta. And again, this is super convenient because you can see that if theta is our variable, let's use a different color here, then this thing is a constant with respect to theta. So the antiderivative again is easy. It's that constant times theta, evaluated from 0 to 2 pi. If we plug 2 pi in, we're going to get 2 pi times this quantity. We plug in 0, it'll just go away. So then finally we end up with the integral from 0 to 2 of 2 pi times 2r cubed minus r to the 4th dr. So that's not too bad. What we should do is maybe just move this constant out in front. Let's put this 2 pi out here so we don't get distracted by it. Integral 0 to 2, 2r cubed minus r to the 4th dr. We plug, do our antiderivative finally. What do we end up with? We end up with, looks like a 1/2 r to the 4th. Oops. Hold on a second. R to the 4th minus 1/5 r to the fifth, and then this is going to get multiplied by 2 pi as we evaluate from 0 to 2. So plugging in 0 is going to kill everything. We're just going to plug in that 2. If we do this math correctly, we'll get 16 fifths of pi. Okay, great. Thanks for watching.